Welcome to Module 2. In this part of the course, we'll explore differential equations, one of the most important mathematical tools for describing how things change. While linear algebra helps us handle structured systems of numbers and transformations, differential equations help us understand change over time or space. They appear everywhere. In physics, to describe motion, heat, and waves. In engineering, to model control systems, vibrations, and electrical circuits. In biology, to study population growth or the spread of diseases. In economics, to model market changes and investment growth. Our goal in this module is to understand what differential equations are, the different types you'll encounter, and methods for solving them. We'll focus first on first-order equations, then move to second-order equations. Along the way, we'll interpret solutions, connect them to real-world scenarios, and discuss how to visualize their behavior. 1. Introduction to differential equations and their applications. A differential equation is simply an equation that relates a function to its derivatives. A derivative represents the rate of change of something. For example, velocity is the derivative of position with respect to time. So, a differential equation connects a quantity to its rate of change. Differential equations can be ordinary differential equations, ODEs, where the function depends on only one independent variable, such as time. Partial differential equations, PDEs, where the function depends on multiple independent variables, such as time and space. In this course, our focus will be on ordinary differential equations, first and second order, since these are foundational and widely used in engineering. Why learn them? Because many engineering and scientific problems involve change. The cooling of an object over time follows Newton's law of cooling, a first-order ODE. The motion of a spring mass system follows a second-order ODE. The charging and discharging of a capacitor in an electrical circuit are described by ODEs. 2. First-order differential equations. A first-order differential equation is one where the highest derivative that appears is the first derivative. In plain words, the equation only involves the function itself and its first rate of change. We will study 4 key aspects here. Geometrical considerations. Isoclines. Separable equations. Integrating factors. 2.1 Geometrical considerations. When you can't solve a differential equation exactly, it's still possible to understand its behavior using geometry. Imagine you're looking at a slope field, a plot where each point in the plane shows the slope of the solution curve passing through it. This slope tells you the instantaneous rate of change at that point. If you pick any point and follow the direction of the slope, you trace out a possible solution curve. This helps you visualize how solutions behave without doing any algebra. 2.2 Isoclines. An isocline is a curve along which the slope of the solution is constant. Why are they useful? Instead of drawing the slope field point by point, you can draw curves where the slope has the same value, for example, all places where the slope is 0, or all places where the slope is 1. By connecting these curves, you can more easily sketch the behavior of solutions. This approach is especially handy for qualitative analysis, understanding stability and trends in systems. 2.3 Separable equations. A separable equation is a type of first-order ODE where you can rearrange terms so that all expressions involving the dependent variable are on one side, and all expressions involving the independent variable are on the other. Once separated, you can integrate each side with respect to its own variable to find the solution. This method appears in many physical problems, such as exponential growth and decay, where the rate of change of a quantity is proportional to the quantity itself. 2.4 Integrating factors. Not all first-order equations are separable. Another important type is the linear first-order equation, which can be solved using an integrating factor. An integrating factor is a special function that, when multiplied through the equation, transforms it into something you can integrate directly. This method is essential in electrical engineering for solving equations that describe resistor-capacitor circuits, and in mechanics for systems with damping. 3. Second-order differential equations. A second-order differential equation involves the second derivative, the rate of change of the rate of change. These are common in physical systems where acceleration or curvature plays a role. 3.1 Introduction and motivation. Second-order equations naturally arise in mechanics, such as Newton's second law of motion, where force equals mass times acceleration. Vibrations, like those in bridges, machine components, or electrical signals. Electrical circuits, especially those involving inductors and capacitors. 3.2 Homogeneous equations. A second-order ODE is homogeneous if every term involves the dependent variable or its derivatives, and there are no standalone functions of the independent variable. The solutions to homogeneous equations often involve exponential or oscillatory functions, depending on the system's damping and restoring forces. 3.3 Non-homogeneous equations. If an extra term appears that depends only on the independent variable, such as a driving force in a mechanical system, the equation is non-homogeneous. The solution in such cases is the sum of the general solution to the corresponding homogeneous equation, a particular solution that accounts for the extra driving term. 3.4 Applications in physical systems. Example 1, spring mass system. The oscillations of a spring mass system are described by a second-order equation. If there's no external force, the system may oscillate forever, ideal case, or die down over time, with damping. Example 2, RLC circuit. An electrical circuit with a resistor, inductor, and capacitor also follows a second-order equation. The voltage and current behaviors mirror the oscillations of a mechanical system. Example 3, beam deflection. In civil engineering, the bending of a beam under load is described by a second-order ODE, relating load distribution to displacement along the beam. Module 2 Summary. In this module, we explored first-order and second-order differential equations, both in theory and through practical examples. We saw how geometrical tools like slope fields and isoclines help visualize solutions. Separable equations can be solved by rearranging and integrating. Integrating factors handle first-order linear equations. Second-order equations appear naturally in physical systems. The difference between homogeneous and non-homogeneous equations shapes the type of solution we get. By combining the linear algebra skills from Module 1 with the differential equation methods from Module 2, you now have the mathematical foundation to model and solve a wide range of engineering problems.